Hello, everyone, and thank you for taking the time to come to learn more about our project, Resilient Life, an exploration of perturbed autopoietic patterns in Conway's Game of Life. The collaboration for this project began during the 2019 Santa Fe Institute's Complex Systems Summer School, and we're so excited to have the opportunity to share it with all of you here today. Our project explores autopoietic systems within the cellular automaton Conway's Game of Life. For those of you less familiar, autopoietic systems were first characterized by the Chilean biologists Umberto Maturana and Francisco Varela in the 1970s, and they are living systems that can self-generate and self-maintain their structure over time. Within Conway's Game of Life, we specifically chose to focus on what are known as still lifes. These are patterns with evolutionary cycles of a single period. Left on their own, they're the simplest autopoietic systems within the Game of Life, and they offer a wonderful starting point to explore autopoietic systems. What happens if these still lifes are disrupted in some way? Are the patterns resilient to disruptions or shocks, in that they can return to a stable state? Are they able to maintain their form and function? These questions, to get you thinking, lead us to the research goal of our project. Ultimately, we wanted to answer two questions. For the first question, we were interested in whether still lifes in Conway's Game of Life are resilient to specific types of perturbations. And if so, what are the structural properties of these patterns that facilitate resilience to our specified perturbations? And not to worry, I'll explain what I mean by perturbations momentarily. Then, for our second question, at a more general level, is resilience a universal property of computational systems? To answer our questions, we chose to perturb the still lifes to test both additive and subtractive resilience. For the former, we added one or two live cells within the pattern's neighborhood, and for the latter, we subtracted one or two live cells from the pattern. One can think of it as examining both external and internal disruptions to the system. We decided to use three similarity metrics to calculate the resilience of particular still lifes. The first one, our equality measure, was simply whether the still life returned to its original pattern. In other words, was the resulting still life able to return to its original form? The second one, our inclusion measure, looked at the extent to which the still life absorbed, or incorporated, the perturbation into its resulting form. While our last measure, a cosine measure, allowed us to see the amount of overlap between the initial still life and the resulting still life. Our experiment involved perturbing approximately 160,000 still lifes recorded in the publicly available Katagolu. We've made the code used to conduct our experiment available for free on GitLab. And you can see the results of our experiments in tables 1 and 2 and figures 2, 3, 4, and 5 located in the center of our poster. In the interest of time, I'll mention just a couple of the results and give you all time to review the poster and ask additional questions during the Q&A period. We first ranked each still life by the three self-similarity metrics. As we show in table 1 and figures 2 and 3, which you can find at the top of the middle of the poster, still lifes that were ranked highly on one similarity metric were rarely ranked highly on the other metrics. Further, no still life was the most resilient to more than one type of perturbation. That said, we found exponential decline in resilience across the similarity metrics at a given rank for both additive and subtractive perturbations. This suggests to us that in this system, still life tends towards brittleness. Considering the structural features of the still lifes, we found that the number of connected components, population size, and a pattern's density were the strongest positive predictors of resilience for still lifes. So to return to our original research questions, with regards to the first question, we found virtually no still lifes were resilient to both additive and subtractive perturbations. This suggests to us that systems have specific types of resilience to unique disruptions, rather than a more general resilience. We were surprised symmetry did not facilitate resilience to our specified perturbations. However, we did find higher density patterns were more resilient. This suggests to us that as still lifes approach their carrying capacity, or perhaps their autopoietic limit, they become more resilient. Our second research question, however, remains unresolved. We could not determine from our investigation whether resilience is a universal property of computational systems. Thank you all so much for your time. We'd love to hear your feedback.